Hi everyone, I'm Will Conrad, the Mining Technical Lead for Canary Systems. This lesson will be discussing the process of integrating monitoring data, such as from ground-based radars and INSAR, with numerical modeling and the iterative cycle that can be performed between the two. The reasoning behind this is really twofold. One, to validate models and be sure that your predictions and estimates are within reason, and two, to help understand the data you're collecting in real time or near real time to take appropriate actions. In the course of this presentation, we'll dive into how this process has typically been handled in the past with the introduction, what the basis is for the integration, how the integration is accomplished, and what materials need to be prepared. We'll also look at a few key considerations that need to be thought out, and finally, an example of how this compilation appears in a data integration platform. To begin, the process of updating numerical models has typically been a one-way street, where data from the field is collected. Calculations are performed to have meaningful values to work with in engineering units, and then the data is fed into the modeling software and the results distributed to the appropriate parties for decision making. Besides the number crunching in the modeling software, this process has largely been manually performed due to limitations in the amount of effort to get systems to talk to each other. Advancements in integration platforms using browser-based applications, which have become a standard, now allow 3D visualization with generic data imports of XYZ coordinates with unlimited amounts of metadata associated with each point. This is perfect for showing ground-based radar data, INSAR data, and numerical models in one location. Really, the goal of these efforts here are to work together to validate to improve models to better predict ground responses for a safer working environment and understand what can and can't be done within the framework of operations and design. These days, data from the field can be collected remotely, validated, and processed through calculations, with results fed into a software for modeling. In return, after the modeling techniques are applied, the results can be fed back into the integration software to join the most current data from the field for validation of both the model and of the collected data, to then cycle and refine again. The integration software, which is the literal heart of the process, is what sucks the data in from the various sources, pushes it out, and brings it back together again. For many data types, the entire cyclical process can be largely completed with little to no human interaction after an initial setup. Once you're confident in your setup, the cyclical process can be handled in a near real-time basis with data import and export intervals scheduled for whatever time period you wish. Processing of the models is likely going to be the longest part of this equation, depending on how much data is fed into them. This said, you of course still need to periodically review each step within the process to make sure that the field data is being validated appropriately, the correct parameters are being input into your model, and that modeling results resemble what's actually happening in the field. Often you perform these checks to relate to how confident you are in your deployment. Also, be sure to, before inputting any monitoring data into a model, that you fully understand the limitations of the data type and take them into account. This process also allows a way to bring together remote and point data to help remove the effects of the limitations of each and highlight their advantages. The point data is of course limited to defined locations. It doesn't cover the entire area of monitoring need, while remote data can be limited by line of sight issues. One result from these two plus sources of data can be modeled using the data from both. In other words, we can take into consideration the advantages and limitations of all inputs available for an area of interest to provide the most appropriate information for analysis. Here are just a few examples of the types of numerical models that can be integrated with monitoring data to help better understand geotechnical conditions. It's important to note that models can be surface-related, subsurface, bench scale, pit scale, and so forth. For what constraints you'll have with the integration of monitoring and modeling data, it depends on what you want to analyze, the types of monitoring you're performing, and the amount of other data sources available for integration. What we're seeing here in the pictures of an open pit are modeled yielded percent at the top and a cross-section detail of the factor of safety at the bottom. Next, we'll dive deeper into the workflow to implement a monitoring and modeling data integration. Before you begin, you'll want to brainstorm and gather all the relevant collateral that is available and can contribute to the stability of an area you wish to better understand. You'll then want to consider the locations where this information is housed, export capabilities from the systems compared to the import capabilities of your integration software, and how the actual process will look to extract, integrate, and feed the information into the modeling software. From there, the export capabilities need to be reviewed for the modeling software to effectively integrate that resulting data back into the integration platform, where the monitoring and modeling data types should be compared with each other to validate both. Theoretically, these should relate if you're collecting good monitoring data, inputting applicable and correctly assumed parameters into the model. The data flow process then repeats as conditions change and models are refined with more data or tweaked with more accurate assumptions. So what did I mean by collateral in the last slide? Collateral can include data trained models, known as DTMs, monitoring data itself, other types of data such as inspection results, borehole logs, and other models that are related to geotechnical analysis, but maybe not a part of the continuing cycle of data flow. An example of this could be a geologic model that was created by borehole logs or laboratory results from core tests. DTMs can be in a wireline contour or contoured with a solid surface, depending on the preference of the individual investigating the data. The main item to relay with these is the elevations and slope profiles related in time with the monitoring and modeling data itself. The main consideration when preparing collateral is to make sure that timestamps are overlapping and that time intervals for the data are consistent. You, for instance, wouldn't want a DTM from 2017 showing with data from 2023, or only PRISM data from the last month compared to only radar data from the last week. This can be misleading and can lead to incomplete or incorrect conclusions. Consistent time intervals of displacement data are important as well to more easily understand the data, especially for remote data source outputs, such as from ground-based radars where displacement time period outputs can be selected by a user. For example, having a consistent weekly output of displacement data is much easier to comprehend compared to a mixture of 6-month and 1-week data, where you either have to lose details by focusing on the longer time period or make interpolations to divide the longer time period up to visually compare face-to-face values. You're always going to be mainly limited by your shortest interval of time for being able to gather the most complete picture of site conditions. Since shorter intervals can of course always be combined to equal displacement over a longer time period. Here we have a flow diagram that displays what we just discussed, the inputs and cyclical nature of the monitoring and modeling data integration. The DTMs and other models, such as geologic, are typically imported on a longer interval, such as a month, when enough changes have occurred on site to reason an update due to mining or additional coring. While the point and remote data may be integrated as quickly as data can be read and communicated. This occurs anywhere from a few minutes to multiple weeks, depending on the specific data type. After the data types are integrated together, the data should be validated before being fed into a model. There are a few ways that this can occur. Validation can be automated with mins and maxes, a tolerance of a % change between readings, or a specific set of conditions being met. Subsequent alarms can even be set up alerting users of the significant difference between the data types collected for monitoring and between the data processed by model and the monitoring data. Validation can also, of course, be performed manually by visually inspecting the data to ensure it's reasonable based on either prior experiences or from expected outcomes. After validation, monitoring data can be fed into a numerical modeling software for processing. This processed data is then integrated with the other data types from various outside sources, and the process continues. One of the largest challenges that Cyclical experience with setting up data integrations is figuring out the data formats and how to get the data from A to B. Depending on the software being used and needs involved for the data type at hand, sometimes manual data transfer is all that's possible for integrations. This data may come in directly through as a comma separated value format based off an Excel sheet or a specialized mobile application where the data is physically entered by a user. Many data types are able to be automatically exported for re-import into other platforms. The transfer of CSVs are again a popular basic method for how this is accomplished. Direct connections to data loggers or gateways in the field, as well as direct database imports of automatically collected data are also common, such as through using structured query language or open platform communication type of imports. The way data is probably transferred is through an application programming interface, otherwise known as an API. REST APIs are most common these days, where constraints are made for architectural style of the data transfers and requests are performed over a web service. Softwares usually have to be specifically set up to communicate between each other, and some level of programming is typically involved. There are many different types of ways software can export and import data. There's usually a best solution out there to use depending on the data type, software being used, networking capabilities, and security. Other challenges that occur are knowing where and how information is stored for export. This is especially true for database and API type of imports. Knowing what table or command, if available, to use to retrieve data can be time-consuming if working with a new database. Also, knowing the details of the data is important as well, such as its units and even what a negative reading means. It's usually best to consult user guides or representatives of the company whose product you're dealing with to best configure and figure out these previous challenges. One main final consideration would be the configurations and allowances of your company's IT department. Sometimes ports need to be opened on firewalls or servers that house the data, or user accounts need to be given permission to access certain components. A lot of the time, these items can be accomplished, but there are occasions where, due to security reasons, they can't, and you have to rethink how your data transfers can be rearranged and accomplished. Even though your job may be geotechnical related, it's important to have a good relationship with your IT department to assist when you run into these particular types of issues. Next, we'll move to taking a look at an integrated example of the data types we've been discussing. The example we'll be looking at includes a combination of piezometers, prisms, and TDR cables, ground-based radar, INSAR, and various geotechnical models from an open pit. The integrations, though, can also apply to really any geotechnical application, such as a tailings facility or leach pad. Alright, so we are now in MLWeb, which is Canary Systems' application for viewing and analyzing data. Here I want to walk through the workflow of the integration of monitoring data with numerical modeling data. Let's start with gathering our collateral, which I've already gone through and imported together here. In this example, we have two DTMs integrated from 6 months apart to help us specially identify where we are looking on the property. First, I'll turn on our point data of piezometers and prisms with vectors for you to get an idea of this type of monitoring coverage in our example. We also have one recent INSAR integration of displacement data that covers the entire property, and one ground-based radar integration that covers approximately half the pit. Finally, we have two types of numerical models for a particular area of concern. One of these models displays a cross-section of a factor of safety. The other displays a model of vertical ground displacement in roughly the same area. As far as the actual imports of the remote monitoring and numerical modeling data into the platform, these are very similar in structure. Here the INSAR data was imported in from a geo database, while the ground-based radar data and numerical models were both imported using a CSV format. Even though the header information is slightly different between the various data sources, the data sets were organized using an XYZ metadata value arrangement associated with particular end date. For data such as displacement, cumulative or incremental displacement may be imported. With all of our data being georeferenced, including the point sensors, it then allows us to easily validate and compare between the data types. When you're mainly looking at the point cloud data from the remote monitoring sources, various tools can be used to help recognize areas of potential concern. These include data point coloring, size, and opacity. For the coloring, it's good to be mindful of what colors are representing. For instance, here we have red representing movement away from the radar for both the ground-based radar and INSAR, while blue means displacement towards the monitoring equipment. Green are the values halfway between these bounds, which with the way I have this example set up means relatively no amount of movement was detected during the data's time frame. This can be somewhat confusing since the coloring of the data depends on the point of the property and the area is being analyzed from. To make this more straightforward, I would recommend working with processed data in defined cardinal directions if that's available. You can also see here that adding a lot of different data sources can easily get overwhelming. One way to help pinpoint areas of concern is to make the opacity or point size of data that's insignificantly changing an opacity of 0% or a point size of 0. This only leaves the areas of significant change visible. So now let's move on to how data can automatically be validated by the system and send out alerts. The simplest way to do this when comparing monitoring data to your modeling data is to find averages of the data within certain bounds. What I'll do here is first filter to a certain area of concern that is showing in the monitoring data. I'm just going to choose a nominal sized area This can be down to perhaps a square meter. You can have multiple areas being processed at the same time. Let's now chart this data. I've ended up selecting all the point data in this area, as well as a few point sensors. One item to note is that the data in this particular demo database isn't following my recommendations from earlier of having overlapping time series between the data sources and consistent time intervals. For instance, our INSAR data is using an interval for displacement of approximately 1 week over a 6-month period, while the ground-based radar data is only one output for a total of 6 months of displacement. While you can visually see the changes in displacement in the point cloud, our actual data ends up being in 2 different scales that need to be considered when reviewing here. I was also unfortunately only able to gather one time series of modeling data from this particular area, so that's why you're not able to see a time series here for it either, but hopefully you're able to understand the idea and capabilities of this process. So back to how we can set up an automated validation method. For this example, I've grabbed the bounds of the ground-based radar and the INSAR data, both showing a cumulative displacement. Then I'll create a calculation outputting the differences in these values. Since these 2 values are both in inches of displacement, I'll keep things simple and purely subtract one value from the other. More complex comparisons can of course be accomplished. In-platform alarms and output notifications, such as by email, can be configured based off of this resultant to automatically alert the user that values have been determined to be a certain significance different. This allows the user to further analyze why this occurred to make adjustments for more reliable future data collections. The same process of comparisons can be done with the monitoring data in numerical models, really whatever interval data is being imported and exported at, whether it be hourly, daily, or some other interval. We'll now move back to the presentation to summarize what we've discussed. In summary, monitoring and modeling integration can be handled in a cyclical, near real-time process. The integrations allow the validation of both the models as well as the monitoring data itself to provide the checks and balances in a dynamic system. And finally, when implementing this process, it's important to consider where your data is stored, how it can be exported and imported, and how different software can communicate. Software vendors in your IT department are going to be critical in helping determine the best way to deploy the cyclic integration. This concludes our discussion on the process of integrating monitoring and numerical models using a cyclical approach. If you have any questions about this presentation, please post them to the discussion board on the D2L course site or email them to gce@arizona.edu. Thank you for your time.